Very warm welcome to everyone out here. Welcome to our course of marketing research and analysis second part. So, as in the last class we were discussing about hypothesis development and the errors that we usually face during hypothesis testing. So, the type 1 and type 2 error, and there we came across something important equally was the power of a test. So, we had stopped there and we are today continuing in this lecture 5 in the about the power of a test and then about sample size calculation in during a hypothesis testing. So, today we will go through it. So, let us see what exactly is the power of a test. If you remember last class we spoke about this two errors, one when the hypothesis was true, false, and it was accepted and rejected. So, when it was true and accepted, so it was okay. When it was true but rejected, so it was we said alpha or a type 1 error. Okay. Similarly, when it was false but accepted, it was again a mistake and we said this mistake is called a beta or type 2 error. Okay. And this was again the correct. So, when we said about this beta is the type 2 error. So, we said 1 minus beta is what is called as the power of a test. So, what is this statistical power? It says the ability to find a difference when one really exists. The higher the power of a test, you can say the stronger the test is. In simple terms, we can understand it this way. Let us see. So, what it is saying? The probability of rejecting a false null hypothesis. So, as you saw in the first initial slide. So, we said the type 2 error was accepting a false null hypothesis. So, power is 1 minus accepting a false null hypothesis. So, that is what it says, the probability of rejecting a false null hypothesis. Okay. Similarly, the probability of obtaining a value of t or z whatever that is large enough to reject S0 when S0 is actually false. So, you need a substantial significant value so that you can claim ki no, this is wrong and it is not to be accepted, right. We always test the null hypothesis against an alternative that we have already discussed. Usually the goal is to reject the null hypothesis in favor of the alternative, that also we have discussed ki any researcher whenever he tries to conduct a research or does a hypothesis testing, the major purpose generally speaking, it is not always, but generally speaking in any at least in marketing research and market related studies, it is to disprove or reject the null hypothesis and accept the alternative hypothesis. So, the researcher is more interested for the alternative rather than the null, you can understand it this way. What is this power? Now, let us come to the discussion. Power is probability. So, the number as any probabilistic value lies between 0 and 1, right. So, if it is, as you can understand, if it is towards 0 it is poor, if it is towards 1 as close to 1 it is better or stronger, right. So, 0 is bad in simple terms, 1 is good. Okay. Need to make power as high as possible. So, the intention of the researcher is always to have the power as much as possible, right. Why? Because you are rejecting a false null hypothesis, right. So, that is why. So, the intention is to make the power as high as possible, right. So, how do you maximize power? So, the true value of the parameter, if you understand the true value of the parameters are maybe the mean, the standard deviation, variance, the true value when you can calculate, you can understand and then accordingly your power of the study will increase. Similarly, the higher the significance level. Now, we have earlier also discussed that alpha and beta are related, right. So, if your alpha is high, beta will come down slightly, right. Similarly, vice versa. Now, as you have a higher alpha, automatically you have a lower beta. So, what happens as a net result is your 1 minus beta becomes higher, right. So, therefore, the higher the significance level, higher the type 1 error, the lower is the type 2 error and therefore, the higher the power. Okay. Extremely low alpha leads to very high beta errors, right. Thus, lower power of the test, as just I explained. If your alpha value suppose is at a very low level, right, 1 or even 0.01 or something, then alpha and beta are like a swing, alpha and beta are like a swing. So, they cannot be the same. If alpha is going down, beta tends to go up. So, as it tends to go up, a very low alpha will lead to very high beta errors, thus the power of the test will go down, since power of the test was beta, okay, 1 minus beta. Direction of the test. Now, the direction of the test also has an influence on the power of the test. Now, how that happens? Let us see this. Now, when you have a two directional test, so the test is divided into two sides. So, in such conditions the power of the test becomes slightly low, right. In comparison, when you are interested, when you are very clear with the direction or the orientation of the study. So, when you are interested in the orientation, you are interested maybe for either one side only, there in that case the power of the test becomes more robust. You can logically also think, because you know the direction. In the earlier case, when it was two directional or non directional, you did not know which side the test is moving. Therefore, when you are clear, logically the power of the test, also the strength of the test improves. Okay. The smaller the standard deviation, higher the power. This is another relationship between power and standard deviation. The larger the sample, the higher the more the sample size increases. As sample size goes on increasing, the power of the study goes on increasing, right. So, the best way to improve the power of a test is to increase your sample size, you can be sure about that. Facts. The researcher is free to determine the value of alpha, we have already discussed significance level or alpha, right. The experimenter cannot control beta, since it is dependent on the alpha. You always, I have said in the first lecture series also, that we are testing the null hypothesis. What we are doing? We are testing the null hypothesis. Okay. So, when we are testing the null hypothesis, we are testing it at a particular level of alpha or the significance level, correct, or at a confidence level. So, what we are saying is the study is dependent on the researcher who decides the alpha. So, as we cannot control the beta, we are dependent on the alpha, right. The ideal situation is to have alpha as small as possible and power close to 1, right, but very low alpha also will create very high problems. So, what you do is the ideal situation, it is saying the ideal, this is the ideal situation, is to have alpha, a small alpha and the power close to 1, and statisticians have found out when the power is greater than or equal to 80%, it is considered to be a very strong or a good test. Okay. So, that you can always check. Alpha increases, the power increases, right, but also the chance of a type 1 error has increased. Okay. Best way to increase power without increasing alpha is to increase the sample size, this just now I explained. Why is power important? As researchers, we put a lot of effort into designing and conducting a research. This effort may be wasted if we do not have sufficient power in our studies. That means, you do not have the power, means you cannot reject a false null hypothesis. So, when you cannot reject a false null hypothesis, that means you have accepted a bad product in the market which is very dangerous, right. So, this is what is the effect of interest for consumers and researchers. So, power is the ability to detect a real effect, it is measured as I had said 1 minus beta, right. So, this is the situation. To discuss power, we need to understand the variables that affect its size. The alpha level set by the researcher, we discussed it, sample size and the now what is this effect size? Let us discuss this one. Okay, this has already been discussed, but still an increase in alpha from let us say 0.5 to 0.1, that means 5% to 10% artificially increases the power of a study. Now, when alpha is increasing, we said beta will decrease, and as beta will decrease, the power will increase. Okay. Increasing alpha reduces the risk of making a type 2 error, but increases that of a type 1. Increase the risk of making a type 1 error in many cases may be worse Now this is interesting. What is saying? Increasing the risk of making a type 1 error in many cases may be worse than making a type 2 error. Now what is this, which condition? Now let us go back. I had said the type 1 error is a producer's risk. If you remember, it is a producer's risk or a manufacturer's risk. Type 2 is a consumer's risk. Right. So, in case when the researcher feels that the producer's risk is to be given more importance, right, or is of more significance, then in that case he would be more cautious to reduce the type 1 error, right. So, on the other hand, in some cases when the consumer litigation, suppose the consumer files a case or some litigation, goes to the court, sues the company or something, in those cases the companies are more bothered, for example pharmaceutical drugs companies or something. In those cases they are more cautious about the type 2 error, but in a steel manufacturing company or a laptop manufacturing company or something, for example of that kind, generally the manufacturers are more concerned about the type 1 error rather than the type 2 error, because at least if the laptop goes wrong, you have a probability or a chance of getting back the laptop and correcting it, rectifying it, and then giving back to the customer and even making him giving some extra incentives so that he is happy. But what if you are given a wrong drug to the consumer? If you have given a wrong drug, the person may suffer from a severe disease or severe condition, and he might even die or he might have some problem, then he will not be able to, you cannot make him happy again, it is very difficult. So, he would go to the court of law and maybe file a case against you, right, as a company. Example, you see this is an example, replacing an effective chemotherapy drug with one that in reality is less effective. Now suppose you have replaced an effective drug against an ineffective one, then it is a very dangerous case, right. So there in such cases you have to be careful. Power and sample size. Power increases as n increases, I had explained. The more independent scores that are measured or collected, the more likely it is that the sample mean represents the true mean, right. So our idea is, what is power? We said having a strong test, a test which is stronger in the sense that it is explaining the right thing. Now what is the right thing? The right thing is that the sample mean is actually representing the true mean, that is what is actually hypothesis testing. So as you have more number of sample, what is happening is the difference between the true mean and the sample mean will come close, right. As they come close, we say the power of a test has improved, right. Prior to a study, researchers rearrange the power calculation to determine how many subjects or sample size are needed to achieve a certain level of power, usually 80%. So that differs from study to study, okay. Now coming to the third thing that we were saying, what is power and effect size. Now what is effect size? First let us understand. It is a measure of the difference between the means of the two groups of data. Now group 1 let us say and group 2. So the difference between the means, so whatever the means are, let us say G1 bar minus G2 bar is equal to, is the difference, right. So effect size is this difference between the means. So we are saying that it should be as close as possible, right, to represent the population, that means they are from the same population. For example, the difference in mean jump height between samples of volleyball and basketball players, we have taken two kind of sports. As the effect size increases, so does power, right. For example, let us understand, how do you understand as a from a real life in a real terms. If the difference in mean jump height was very large, that means the volleyball players and the basketball players, their jump, right, the jump, let us say the volleyball players are jumping more or the basketball is jumping more, whatever, if this difference is very large, then it would be very likely that a t-test on the samples would detect the true difference. But if the difference is very less, then the test would say ki there is no difference. So the null hypothesis would be accepted. The difference between the jump height jumped by the volleyball players and the basketball players is actually more or less the same, there is no difference, right, and you would not be able to reject that null hypothesis and accept the alternate in those cases, right. So the effect size, higher the effect size, higher is the power of a test, right. So that means the power is ultimately to detect whether that null hypothesis is properly being rejected or not, right, and the alternative being accepted or not. P values I think we have already explained, this is just a repetition of the slides. So, just again just to show you. So, this is the dividing. So, these are the two sides. So, we have kept this earlier also at 5% maybe 2.5%, 2.5% for a 5% case, right. So, what is this P value? Now, you have seen many a times that the in statistics or in any publication you must have seen that nowadays they are writing the P value. Now, what is this P value and what does this indicate basically? The P value actually tells is a test of significance which finds the probability of getting an outcome as extreme or more extreme than the actually observed outcome. Now, let us understand what is the meaning of that. So, if this is the the test, so we are saying what is the probability of the value lying to the extreme corners, to the extreme corners. So, it says what is the probability of getting an outcome, the result whatever the mu, as extreme or more extreme than the actually observed mu, right. So, the actually observed mean. So, it could be the mean, it could be any other parameter also. So, what is this probability? So, if the probability is very low, let us say the probability of getting this value is very low, then that means it is very close to the this end, right. So, when it is very close towards this end or something, then we say the probability if it is less than 0.5, let us say 0.05 at a 5% for a 5% level of significance study. So, if it is very low, then we will reject the null hypothesis. What is it saying? Now, let us look at it again. The probability of getting an outcome to the extreme ends. If the probability of getting it at the extreme ends is high, right. So, we will accept the null hypothesis, but if the probability of getting the value to the end at the extreme end is very low, then we will reject the null hypothesis. Let us say, let us see this. A direction or directions that count as far from what we could expect are determine the alternative hypothesis. The probability assuming that H0 is true, that the test statistic would take a value, let us come back, assuming that H0 is true, that the test statistic would take a value as extreme or more extreme than that actually observed is called the P value. That means if your P calculated value somewhere here and your probability P value is lying somewhere here, that means you are rejecting the null hypothesis. Okay. The smaller the P value, the stronger the evidence against H0 provided by the data. That means if it is a very low P value, we would reject the null hypothesis and accept the desired alternative hypothesis. But if the P value is let us say at is more than 5% for in generally most of the cases, then you cannot reject the null hypothesis, rather you accept the null hypothesis, or you cannot reject the null hypothesis. Let us not say accept, because saying accept the null hypothesis is a wrong way of explanation. So, we will say you cannot reject the null hypothesis. Okay. So, as I was let us understand this P value. What is this P value? As it is saying, the probability that H0 is, assuming that H0 is true, that the test statistic would take a value extreme, as extreme or more extreme than the actually observed. Now, how do you understand? The smaller the P value, the stronger the evidence against H0 provided by the data or the null hypothesis. Let me explain you through a diagram. This is to be very clearly understood. Now, how do you check this P value? For example, let us say, let us take this, right. So, you have calculated, now how do you find out this P value? Now, let us say you have taken a alpha of let us say 2.5%, 2.5%, okay. Now, your let us say calculated value is maybe for example 1.25, okay. Now, 1.25 plus or minus has a, the area under the curve is equal to, if you go to the Z table you will find out that it is something around 0.394 sorry 0.394, right. So, now 0.394 is the area under the curve, that means what, in both sides, right, both sides 0.394, 0.394, right. So, that means what, 0.5 minus 0.394, that is equal to something 0.105, right, 105 something around this. So, this is the value that you have calculated, right. Now, your value is lying, that means somewhere around here. Your rejection region, this is the this is the rejection region, this is the acceptance, not rejection or acceptance region, right, acceptance. Okay. So, if your value has come somewhere here beyond, then that means you cannot reject the null hypothesis. That is why the lower the p value, had my area under the curve, this value which is dependent on this calculated value statistic would have come, let us say, instead of 1.25 it would have been, let us say, 1.7 or 8, and the table value corresponding, let us say, is area under the curve is, let us say, 0.497, right. So, in this case what is happening, if I am subtracting 0.5 minus 0.497, then this is giving me 0.0, let us say, let me do it, 0.5497. So, it is 300, correct. So, 0.003. So, now 0.003 is falling somewhere which your the limit of significance which you had declared as a researcher was 5%. So, or in this case, let us say 2.5% here. So, it is coming somewhere here to the extreme end of the distribution, normal distribution. Then you say that I cannot accept, I am rejecting my null hypothesis because it is falling into the rejection zone. So, this clarity is very, very important for any researcher. How do you calculate this p value, how it is different from the alpha, right. So, this is what needs to be very clear. Then we move on as to the next slide, right. Yeah, let us see, it is written out here. The p value is compared to the significance level, and on this basis the null hypothesis is either rejected or not rejected. So, you have it, right. So, let us say the alpha is, this is the alpha, okay. If p value is less than the significance level, so your alpha is equal to 5%. If p, as I said, is two conditions, is p is greater than, p is less than, right. If p value is less than the significance level, p is less than the significance level of, let us say, 5%, right, the null hypothesis is rejected. So, you are rejecting the null hypothesis on basis of saying that since my probability of occurrence at the extreme ends of the parameter is less than 5%, whatever significance level I have taken. So, I am rejecting my null which says that there is no difference, no change, and accepting the alternate rather which says that there is a change, there is a difference, right. On the other hand, vice versa, if p is greater than alpha, that means this is alpha, if p is greater than alpha, somewhere this side we say understand, then we would not be in a position to reject the null hypothesis, and we would therefore say that there is no change or no difference in the study, right, which is not of concern or interest actually to the researcher. Yes, there are some special cases where I will say explain later on, maybe where the researcher is interested in accepting the null hypothesis, but 99% in generally in any marketing condition or any economic condition, we are interested in always accepting the alternate, right. What are the common misinterpretations of p values? The p value is not the probability that the null hypothesis is true. The null is either true or not, it does not talk anything about that, right. Also 1 minus p is not the probability that the alternate hypothesis is true, right. Correct interpretation is the p value is the probability of getting a value as more extreme than the value of the statistic computed from the collected data. So, you are saying simple terms, let us not get into too much of complication. The p value says where is the outcome lying in the distribution. If the probability of it should lie at the extreme ends. If it is lying, if the p value is very, very less, it is let us say less than 1% or less than 5% as per whatever significance level you have taken in comparison to that. If it is much lesser than the significance level, then we say we will reject the null hypothesis and accept our desired alternate hypothesis, and otherwise the vice versa, the reverse. So, below are guidelines. P value is less than 0.01, evidence against S0 very strong. P value lies between 0.1 and 0.5, moderate, right. P value lies between 0.5 and 1, weak. the evidence against the H0, that means you cannot reject H0, evidence against H0 means you cannot reject, that means you cannot reject H0, right. And if it is greater than 10 p value, then practically you cannot reject the null hypothesis. These three at least you, this is so very clear, this is you, the researcher can think on these two situations, right. But finally we need to understand that p value is a very significant way or a good way of understanding whether to accept or reject a hypothesis, right. Now what we will do is we will start we will get into the next part, which is calculating interval estimates of the mean from samples, or there are different conditions, large samples, small samples. So the first case is a case where I am trying to calculate the interval estimate. Now what is this interval estimate? Now we have understood, like a class interval, what is the range? What is the range of the value, right? So there is a maximum value, there is a minimum value. So we are interested what is the, let us say, of a class IQ, what is the minimum IQ level, what is the maximum IQ level. So is the average of the class IQ lying in between these two or not, that is of interest. So this is like a line where let us say you have the mu here and you are, this is the lower limit and this is the upper limit, and you are interested to see just whether, if I know my lower and upper limit, I can say whether my mu is lying between these two or not, right, or which side it is tending to move, right, this side or the upper toward the lower. So let us take a first case. The first case is a case where the population standard deviation is known, the population standard deviation is known. Now we are always, I have always been repeating that the researcher is always interested to know whether the sample is actually representing the population or not, is it a part of the population or not in all the studies. So go to the first question. A large automotive part wholesaler needs an estimate of the mean life it can expect from windshield wiper blades, okay, under a typical driving condition. The management has determined that the standard deviation of the population life is 6 months. Suppose we select a simple random sample of 100 blades. So simple random sample of 100, collect data on the useful lives and obtained x bar is equal to, what is x bar? X bar is always the sample mean. The sample mean is equal to 21, right. Because the wholesaler uses tens of thousands of these wiper blades annually, it requests that you and me we find an interval estimate with a confidence level of 95%. So he wants to know what is the life of this wiper blade at a 95% confidence level, so that it can, because it is using in large bulk, so it can decide in the future whether to get it from the same supplier or not, okay. So in this condition what will you do, how will you find out this interval, right. Let us see the solution. The sample size is greater than 30. First you have to see whether sample size is less than 30 or greater than. If it is less than 30, it is a case of t test or t distribution. If it is greater than 30, it is a case of the z distribution. So since it is greater than 30, the central limit theorem allows us to use the normal distribution. Had it been less than 30, it would it is not the same, right. So as it is more than 30, ours we are using a normal distribution, and as a sampling distribution, even if the population is not normal, it does not matter, it says what it means is the sample size is greater than 30. So the central limit theorem allows us to use the normal distribution as our sampling distribution even if the population is not normal. The line is slightly it is not readable, that means let us understand we are using the normal distribution in this case, right. So how to calculate the standard error of the how to calculate standard error. Now what is standard error? Standard error you may understand as the standard deviation of the population, right, of the sample, sorry, standard deviation of the sample group, right. So why it is required, why should you calculate the standard error? Because standard errors need to be calculated because it talks about a series of samples and their distribution patterns, right, a series of samples and their distribution patterns. So this is very important for you to calculate. Now how it is calculated? It is nothing but a ratio of the standard deviation upon the root over of sample size. So, in this case our standard error of the sample, the distribution is 0.6 month, 6 upon 10. So, it is 6 by root over of n. Now, root over of n is 100. So, that is equal to 6 by 10, that is equal to 0.6 month with 95% confidence level. Now, you do not know which side of the hypothesis it should go, which side of the tail of the distribution it should go. So, when you do not know, it is a two tail test. So, what we have done is the tail has been distributed into two parts. So, 2.5 this side, 2.5% this side. So, therefore, this is actually 0.5, this is 0.5, that makes 1, correct. So, 0.5 minus 2.5 is 47.5% this side and 47.5% this side. So, 0.475 of the area under the normal curve is contained between the mean and a point 1.96, that is the z value, the table value is 1.96 standard error, right, out to the right of the mean. So, therefore, that is equal to let us say now let us find out the confidence limit, right. So, 2 into 0.4 as I explained in the last slide, 0.95. So, it lies between z is equal to 1.96 negative to plus 1.96, because this is for a 95% confidence level, the z value is 1.96, right. Now, how do you calculate? Let us see this. So, x bar plus z sigma bar, right. So, what is your this part, you have it, right, and x bar. So, x bar was a sample mean which is 21 months plus minus z is 1.96 into sigma x is, you have calculated something 6 months I believe, 0.6 months, right. So, that gives us a value of 19.82 on the lower limit and 22.18 on the upper limit, right, and your mean it was 21 months, correct, 21 months which lies between these two. So, in such condition we will say that this is the upper limit, and such a condition you can even assume that the null hypothesis is to be not rejected and it lies within the boundaries of the extreme values, that is the class interval, right. So, this is the first case, this was case 1. What we will do is we will follow it up in the next lecture and we will continue with some more examples and more conditions. I hope this lecture was clear to you. Thank you so much.